Morning, everybody.
Good morning.
Welcome to the last week. Right? Okay, so time to stress you out. Today we have review. Thursday we have the exam. And then you will, for all intents and purposes, be done with this class, right? You just have a test autopsy to do. But really, once this exam is taken, it's kind of in the bag. Tomorrow's lab isn't. Right, like homework is done. I always leave that last week. Again, as a little bit of a pressure valve for you. I will be here. I will be in the lab room if you want to come and form your cheat sheet together, or just make whatever. Use me, abuse me. I will be around, and my first focus will be you if you're in the room. If you're not, I've got plenty of other things I'll be doing, but happy to help you. If you can spend that time better doing something else, do that, right? There won't be any lecture, there won't be anything going on tomorrow in S260. Your exam autopsy, and I need to post an announcement about this, your exam autopsy is going to be on Tuesday next week. Right, Tuesday, 8 o'clock in the morning, right here. So, is anything happening Wednesday or Thursday next week? No, right? You only attend that, the Tuesday, 8 o'clock in the morning.
What time is that going to end?
How long does it take you to do an exam autopsy? Usually, most people are done in 45 minutes to an hour. So. But it will definitely end in 2 hours because we have to keep to the final schedule because you've got other classes and the other classes are going to want to come in here and blah 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 blah. So just be aware of all that. Questions, comments, and concerns about this week and the exam autopsy next week. How's your finals schedule lining up? You guys have all your finals on exactly the same day? Yeah, so you're like, others of you are like, finals? My worst finals day was 4 finals on the same day. That was actually by choice because I was allowed to, that semester I was allowed to kind of schedule when I took my finals, and I decided to just get them all done in one day. So that's what I did, and I died, and it was okay. All right, so this exam, where is it? Right there. Okay. So did I do this last time where I organized it by chapter? I did this last time, didn't I? I seem to have some vague memory of this, right? I did try to line it up by chapter and then got horrified that I managed to put 4 questions from fluids. On the exam, but that's what it was, okay? And so what are your questions, concerns, things you would like to talk about? I mean, I know our homework's done, right? And you can go look up the solutions on there. But what can I help remind you of, get you grounded for? One.
So chapter 15, there won't even be a conceptual question at all?
Yeah, I decided, because I didn't give you homework in it, right, there was no chapter 15 assignment, I thought about doing conceptual, but the heat transfer question, quite frankly, was easier, so so I picked that one instead. I hope it's easier, it better be easier. They always seem easy to me. Yeah, nothing on chapter 15. Pure knowledge.
I'm feeling kind of shaky on Archimedes' principle.
Okay, so Archimedes' principle and Bernoulli's equation, right? On both of those topics, you want to have some help on?
You can just pick one.
Well, no, we can do both, right? But I want to make sure first off that they are 2 very different situations, right? That we're talking about. So part of the problem on an exam, right, is being able to identify the question, like where is it coming from, what topic is this on, all that kind of stuff, right? So how do you tell the let's ask it this way. How do you know if it's an Archimedes principle problem? What are like some giveaways? Maybe not. Nice guess though. What was Archimedes all about?
Buoyancy.
Yeah, it was buoyancy, right? So an Archimedes principle problem is going to have something to do with buoyancy, which either means something floating, right, on the surface of water, or maybe it's completely submerged, or maybe it's a balloon in air, but there's going to be a buoyant force involved. And so the other thing that Archimedes principle, Pascal's principle, and pressure at depth, all three of those things have to do with fluid statics. In other words, the fluids don't move. We don't assign a velocity. There's no fluid flowing anywhere, like in a pipe or anything like that. Anytime you get fluid motion, that's going to be Bernoulli's principle, right? Or Bernoulli's equation. So this one needs the velocity, right? There's going to be they're going to ask you, like, what is the speed of the water in the pipe? Or, water is flowing at such and such a speed, and then it goes into a different size pipe. What's the new speed? That's all fluid dynamics because it involves motion, right? So if it's not mentioning velocity, it could be one of the other three. And then again, sort of dead giveaways here, right? I'm not sure I spelled that word right, but you get the idea, okay? There's some sort of buoyant force, right, where we've got that buoyant force is equal to the weight of the fluid displaced. That's going to be Archimedes' principle. They're probably going to be asking you to find density of an object. That's kind of what we did with the crown. You might know some densities and have to find the volume of the object. There's lots of things you could solve for, but the overall problem type is going to involve equilibrium where the forces are balanced, buoyant force will be acting up, gravity will be pulling down. And we did a lot of examples of those. So let's tackle Pascal's principle. The key thing about Pascal's principle is this hydraulic, there we go, I spelled that one right, okay? These are hydraulic systems. Pascal's principle is all about the pressure is equal the same everywhere in a fluid at the same depth, and if you press on one side of the fluid, that pressure is transmitted throughout. And we use the example of being able to lift a car, okay, up on a hydraulic jack or something like that. We're trading like an area, cross-sectional area, in one part of the fluid for a different one other, and the ratio of those areas is what determines how much we can lift the car, right? So this usually comes out as like force and area on one side, force and area on the other side. But it's going to be Pascal's principle if we're talking about some kind of hydraulic system. Lifting an object that's very heavy, something like that. And then pressure at depth, okay? Here's where we have, right, our H. Now, it's not to say that you couldn't have a height. Like, height does come into Bernoulli's equation, doesn't it? Bernoulli's equation is that pressure plus 1/2 rho V squared plus rho GH, right? So there's crossover there. But pressure at depth is specifically all about find that pressure, okay? At the bottom of a lake, where a submarine is 1,000 feet below the surface of the ocean, in Venus's atmosphere, like the pressure that you experience because of the fluid that is above you, specifically. I've noticed time and time again, this is something that is multi-generational, okay? Students typically forget that there is air pressure sitting above, say, the surface of a lake or the surface of the ocean. So if you're being asked to find the pressure at 100 feet below the surface of the ocean where a dolphin is swimming, it's not just rho GH. The rho GH comes from the water, right? It's the pressure that's being produced by the water. But the water itself has atmospheric pressure on top of it. So it can be easy to forget, right, that one atmosphere has to be added onto the thing. So when we're asking for pressure at depth, we're solving for P, where P naught is atmospheric pressure plus the contribution from the fluid that the object is in. But again, it's a fluid statics thing, whereas if you've got Bernoulli's equation, it can involve height, but it's also going to involve fluid motion. Just if it's velocity, then, and it's a fluid and it's velocity, that's Bernoulli's equation. The problem could have height in it, but that's taken care of by Bernoulli's equation. If you're being asked for what is pressure at depth, that's a fluid statics problem, right? And then, I wouldn't do this kind of thing to you on an exam, but what's the difference between gauge pressure and absolute pressure?
Gauge pressure is like the difference in pressure between outside and inside.
Yeah, it's like a comparison. Absolute pressure is what the pressure is. But gauge pressure is a comparison. I always like to think of a tire, right? When my tire is flat and the pressure gauge reads 0, it doesn't mean there's a vacuum in my tire, right? It just means the pressure inside my tire and pressure outside my tire are the same. So pressure gauges always reference ambient or atmospheric pressure compared to the pressure you're trying to measure. Aiden, did that answer your question sufficiently, or do you want some examples?
I think that's something.
Okay. It can be difficult to tell the difference, but those are the key things that you're going to be looking for, right? Yeah.
The buoyancy, are we to always expect that the force pushing up is the same as mg?
No, it depends. Because you could have an object that's suspended by a string, right? And so in air, that string would be opposed by gravity, the tension in the string would be mg, but in the fluid, now buoyancy is, you got 2 upward forces and 1 down. So the 2 ups have to cancel. We always have to cancel vertically in a buoyancy problem. It's an equilibrium problem, there's no acceleration happening. So, yeah, I know you want absolutes and I can't give it to you. Yeah.
Can you do me your 7 in chapter 11?
I could try. It's fluids. Usually pretty good at fluids. And then, how do you tell the difference between the last 3? Like calorimetry, how do you know it's calorimetry? Like specific heats involved, right? Okay, you're either told some specific heats or you're looking for a specific heat, right? But if it's got specific heat in it, it's calorimetry. The heat transfer conceptual is going to be about conduction, convection, or radiation, right? So just know what those mechanisms are. And then ideal gas law, PV equals nRT. Again, there we're changing pressure, volume, or temperature, or some combination, right? So that's how you tell the difference there. All right, chapter 11. You said 7, didn't you, Sally? Ah, yes, the hollow specimen, right? This does happen with pumice stones and other things like that, okay? So we need, part of the problem with this problem. And this, oops, is the way that they want you to answer. I'm not sure why they can't be straightforward and just ask you for the density or something, right? But what they wanted here was the fraction of, what fraction of the volume is solid? And the way I interpret that is that this is the volume of the solid divided by the volume total, right, of the object. I've got this rock sample, right, okay? And from the outside it looks all solid, but there are these like air pockets in there. That was not intended to look like a cell or anything else. All right. So this is what I am after, this ratio. And so I kind of try to keep that in mind, right? And sometimes it's even hard just to figure out what the words mean, right? All right, we are given some density. We also find that the weight in air is twice as much as it does in water. So how do I write that down? That's a piece of data I need to know. So my the weight, right, in water, okay, is twice as much. Nope, other way around. My weight in air is equal to twice the weight in water. Again, I'm not sure how to use it yet, but I am just putting, I'm trying to get some ideas down on the page and give me somewhere to go, right? All right, and then they give me some density, but it's the only density that I've been given. Okay, so let's see where I can go with any of this information. Can I, like what's the weight in air? Object just sitting there, what's its weight? Just mg, isn't it? Right? So I'm gonna write that down. I know that that's mg. Okay. And then the weight in water. So what's going on like in water, right? If I put this thing in my water tank, okay, then I do have, gravity doesn't go away, right? I still have the gravitational force acting on it. But now I do have this buoyant force acting up, right? And the implication when we weigh it in water, there's going to be some sort of tension that's attached to the scale or some normal force of the scale it's sitting on or something like that. And so my weight in water, this tension right here, which is my weight in water, right, is going to be equal to gravity pulling it down minus the buoyant force. I didn't really mathematically do that. I'm just looking at this going, okay, I know it weighs less in water. And why does it weigh less in water? Because the water's holding it up, right? It's got true weight, and then the buoyant force is kind of taking away from that weight to give me my weight in water. Okay, so what's something I know about buoyant force? Is there a way that I can connect the buoyant force acting on this rock with its volume? That's kind of what the buoyant force is, right? Buoyant force is equal to density of, what's the density of what thing? Buoyant force is equal to the weight of the, key conceptual thing here. Maybe I'm not asking the question right. It's not the object. The buoyant force depends on the weight of the fluid displaced. So that means this is going to be density of the fluid times g times volume of the fluid displaced. Make sure you remember that. Buoyant force depends on the fluid that's been pushed out of the way, okay? All right, so what does that leave me with? It means that my weight in water is equal to mg minus density of the fluid times g times volume of the fluid displaced. What's something we know about the volume of fluid displaced? It has to be the same as something. What is it the same as? It's not density, because volume and density are not the same. Really close.
Is it how much it sinks?
No. This object has been put completely in the water. So what is the volume of water that gets pushed out of the way by the object equal to? The object's volume, right? If we put the whole thing underwater, then that's how much water had to get out of the way. And so the volume of fluid displaced in this problem is equal to the volume total for the object. If it had been put halfway in the water, we would have said it was half the volume of the total, right? But here, the entire thing has been put underwater. Okay, so what I'm doing here is I am kind of just throwing ideas at the wall to see what sticks. That's really sort of the problem-solving method here, right? And this problem, I think, is pretty complicated in that there's a lot of puzzle pieces that you have to put together. Right? Okay, so we can go ahead and make that substitution right there. We know the density of the fluid. They told us it's in water. I can go look up the density of water. They don't tell me the mass of this specimen at all, do they? Right? They tell me the density of the solid part, right? So now I want to see if there's something I can do with the masses that I have in this problem. Because they didn't give me the mass, but they did give me the density of the solid part. And it's that solid part that gives this thing weight. So how do we connect densities and masses and is there another way to write mass in terms of density? There must be, Mr. Bailey. You're asking me about it. So from the density definition, I can go ahead and write density times volume. Just again, multiplying both sides by V there. So that means that this M over here can be written as density of the solid part times volume of the solid part times G. All right, I need more paper. Well, maybe I can do it all on the screen. Let's see what happens. So what have I got here? I've got the weight in water, okay, is equal to the density of the solid times G times V, solid part, minus density in the fluid times G times volume total. It's just putting everything together. All right, weight in water. We know something about the weight in water, right? It was right up there, right? It's half the weight in air. In other words, if I divide this by 2, right, I can solve for the weight in air, and since the weight in air is mg, the weight in water is going to be mg over 2 equals density of solid G, all this stuff. All right, I'm almost there. I need to get that mass fixed, and I'm going to fix it exactly the same way I did before. Density of solid, volume solid, G. We've got a factor of 2, G, volume solid. Okay, so now I substitute everything in, and I feel like I might be able to rearrange this to get what I want. Again, I am after that ratio right there. Now I've got some volumes of solids and volumes of total in here, so it feels doable. But first, there's something hanging around that I can get rid of. Little g, right? We got little g in every term. Just get rid of that. That's done. Okay. This is getting a little awkward, but okay. I'm gonna get everything that's got a volume solid in it over to one side. So I want to take this term and move it over here. That makes it negative, which gives me negative. So what's 1/2 minus 1? Negative 1/2, isn't it? So it's negative 1/2 density solid, volume solid. That's that side. And then I've got negative density fluid volume total. Oh, very good. The negative signs go away. I was hoping for that. And then I can divide both. Now I'm just doing math puzzle. There it is. And then I can do density of solid over here, and I can multiply both sides by 2. So that thing, the volume solid to volume total, is going to be twice the density of the fluid all over the density of the solid. I have the density of my fluid, I have the density of my solid. The density of the fluid is water, it's 1,000. And then they gave me the density of the solid. Remember, I'm over preparing you for exams. The exam question is going to be easier than this one, because I consider this to be a pretty involved problem. Again, I did it all symbolically so I could keep track of things in my brain in terms of what the symbols mean. I know you guys like a little bit more of a plug and chug. Give me the equation, I'll solve it for you, Mr. Balogh. And this one requires putting together a lot of ideas in that blank thing. But, all that being said, if you can follow this, you should be able to tackle any Archimedes principle problem that comes your way. This is like the worst it can be. Did I scare you? Yeah.
Can you read chapter 11, number 10?
Number 10. Ooh, same chapter. Airplane. Okay, it's generating lift. Ooh, okay, instantly. Airspeed over the top of, what are we doing? Is air a fluid? Yeah? Is it moving? Yeah? What is this? This is Bernoulli's equation, right? And I'm gonna turn my brain off for a second, because I've just had a big aha moment, and I'm gonna go, oh, Bernoulli's equation, what's that? Well, it's this thing. So plus 1/2 rho v1 squared, rho g h1, and the way that I know all of this is that I've got it on my cheat sheet, right? So I can just look at it and go, okay, all right, that's what it is, right? This has to be Bernoulli's equation because I've got fluid moving. They gave me, right? They gave me a speed there and they gave me a speed there. I've got like 2 different speeds, right? Like a 1 and a 2. So how do I visualize this? I've kind of jumped the gun here and I jumped straight into the equation, but Mr. Bale taught me that sometimes it's easier to start with the equation for Bernoulli's principle and then kind of tie it together. So let's see here. Airplane wing, right? And there's a top and a bottom of the wing. It can be really hard if I drew the airplane like top down view. That's not a very good airplane, right? Okay. So let's draw like side view. So like airplane, right, cockpit, and then like the wing comes out like this, right? So the air flowing over the top of the wing, that's moving at 68 meters per second. And then I've got air going underneath the wing at 39 meters per second. So here I kind of used a picture, right? Like don't judge me for my airplane diagram. To orient myself and my brain about what's going on. The Bernoulli's equation has these things with like 1s and 2s in it, right? And I know that means that I've got to like pick 2 different spots. So the first spot I'm going to pick is over the wings, and the second spot I'm going to pick is under the wings. Again, because this kind of equation where we've got 1 equals 2, whether it's conservation of energy or Bernoulli's equation, it's always this comparison between 2 points. And so I kind of want to know things about those 2 things, those 2 points. Okay. How this is going to help me find the way to play, I'm not sure yet. But my plan of attack right now is, let's see if I can't use Bernoulli's equation to figure something out. But let's see what it can tell me, okay? So the heights are worrying me because the problem didn't give me any like height difference here. So what does that mean?
People like cancel out.
It means it might not be important and that they cancel out, right? Or I'm missing something completely, right? And I'm not getting it. Don't listen to the second voice. I know this is the voice that you like listening to, okay? Because you've been wrong so often in this class. But it's a clue. It's a clue that's being left in the sense that it's not there, right? Okay, the absence of the information or any other way of figuring out like if there is a height difference here between the top and bottom of the wing. The fact that it's not there must mean that it's not important or I don't need to consider it in this problem. I mean, because wings do have a thickness, don't they? Like vertically, right? And so you're like, well, what about that height? Well, the thing is that the air coming over the front of the wing splits, goes over the wing and comes back and joins it on the trailing edge of the wing. So the height difference before and after is still 0. You're like, Mr. Balogh, how am I supposed to know that? Well, now you do, right? But how was I supposed to know that ahead of time, Mr. Balogh? Well, you didn't need to know that. What you needed to realize is that they're not giving you any information on the heights. So it must be the same or unimportant. When you go to cross out something, right? When I cross out this term from this term, I want to make sure that I'm doing it with data, like with information or with some purpose, right? And my purpose here is that I'm going to assume that those 2 heights are the same. And since those 2 heights are the same, whatever they are, 0, 10,000 feet, whatever's going on, because they're on either side of the equal sign, they will cancel each other out. They'll be equal to the same thing. So I always try to leave notes to myself along the way about my assumptions, because sometimes my assumptions are wrong. I gotta go back and I've gotta, try something else. But at least I left a note to myself to figure out just what the heck I was doing. So we took care of the heights. We have these 2 different speeds, right? V1 and V2, that's good. The density is going to be the density of what? Yeah, it's the air density, isn't it? And so I gotta go look that up. They don't tell me what it is. It's annoying. And if Mr. Balogh forgets to give you a density that you need to use, not like one you need to solve for, but like if you need a density in a problem I didn't give it to you, what do?
Ask me.
Suffer in silence. No, ask me, right? Just ask. I'll give you constant, like that. All right, so let's just strike out and see what happens. It's just like, by striking out, I don't mean at the batter's box. I mean like we're gonna go into the forest and see what happens. So I'm gonna move all the pressures to one side. Those P1s and P2s, I don't know anything about them yet. I would like to be able to cancel them out, but haven't been given. Again, there's the absence of information, right? Is that the information? But if we did cancel the pressures out, then we wouldn't have much to do here, right? Like we'd have 0 equals 0, and that's not good. So what I've done is I've moved all the speed terms to one side, I've moved all the pressure terms to the other. And as I look at this, I realize that what it's telling me is that because there is a speed difference there, those two speeds are not the same, there's going to be a pressure difference. How does that help me? What is the question asking me to find? It's right there at the end, isn't it? What's the weight of the plane? Well, it's just mg, isn't it? but they didn't give me the mass of the plane, right? Now, the airplane is in level flight, okay, which implies that it's not accelerating. So, there must be some sort of upwards force that is counteracting gravity. It's not a buoyant force. I mean, yes, the airplane is surrounded by air, okay? But in this case, the buoyant force isn't doing much. It's an airplane, right? Airplanes are way denser than air. So the additional buoyant force that an airplane is getting from the static buoyant force isn't going to do much. So if I can find what that upward force is acting on the airplane, I can find the weight of the airplane. And where is the upward force coming from in an airplane? What part of the airplane generates that upward force? It's the wings. The fact that the wings are moving through the air and that the airspeed is different over the wing versus under the wing gives rise to a pressure difference. And that pressure difference can have a force on those wings pushing the airplane up. Since pressure is equal to force divided by area, I can find that force if I know the pressure. So we're gonna find that pressure, that difference between the pressure, right? This pressure right here, this pressure difference is what I need to be able to find the force that's acting upwards. All right, we're gonna find that pressure by doing this calculation right here. It's gonna be 1/2 times the density of air, 1.29, times V2, which is, I said was beneath the wings, 39 squared minus, I factored out the 1/2 rho because it was in both terms. And then 68 squared. I can see that that's going to end up being a negative number, right? 68 is bigger than 39. But I'm not going to panic too much. It just means that the pressure below the wing is higher than the pressure above the wing, which is exactly what I want for an airplane to go up. So that's good. But whatever that number is, that goes in there. We multiply by the area of the wings, which is given. And then I have the force of lift on the plane, and since the plane is in level flight, that force has to be equal to the weight of the plane. I was looking at airplanes the other day, and I was looking at the largest passenger aircraft in the world, the A380. It's a double-decker airplane. Can carry close to 500 people. In most configurations, it carries about 425. That plane at takeoff has a weight of like 550 tons. 400 of those tons is fuel. How do 550 tons, how does that fly through the air? What must the force on the wings be if the plane weighs 550 tons? Has to be 550 ton force. Matter of fact, it's got to be bigger because the airplane, we don't want the airplane to skip along the ground, we want the airplane to go up, right? And so that lifting force has to be even greater. How do airplanes land? Careful. But it begins by slowing down. As the airplane slows down its airspeed, it begins to sink because now gravity is winning. It's just a question of how fast is gravity winning. In an airplane, you don't want the gravity to win too fast.
So with P1, so if we're using P1 minus P2, would that mean that the P in our equation is going to be a delta P?
Yeah, it's like a delta P. I got lazy with the deltas. Yeah.
Can you do chapter 12, number 3?
12, number 3. Oh, watermelons and soda. I'll have the watermelon, please, not the soda. Okay, ignore speed, chest, and determine final temperature of the soda. Okay, so how do I know this is a calorimetry problem? Specific heats, right? Specific heats are involved. There is an initial surge of panic because I know specific heat sometimes has to do with phase change, like, melting or freezing something, and that gets squirrely. Is there any phase change in this problem? Are we melting or freezing anything? No. Are we boiling anything? No. Boiled watermelon doesn't sound that good. Okay. So, if it's calorimetry, then I'm going to strike out, and using that word a lot today. We got to add up all the Q's and make it equal to 0. So what are all the things that could be gaining or losing heat in this problem? Well, it's pretty obviously that there is a watermelon in here, okay? It's just soda and watermelon, isn't it? There's no liquid water in the ice chest, is there? So I've got a watermelon and then I have all of the soda. That's it. Those two things. Okay. So if that's the case. Q watermelon plus Q soda. What's the Q for the water? What's the heat lost or gained by the watermelon? How do I write that down? Yeah, the MC delta T, right? Which comes right off my cheat sheet. So that's the mass of the watermelon, specific heat of the watermelon, change in temperature of the watermelon. Okay. Plus, okay, now we've got, so we've got mass of soda, specific heat of soda, change in temperature of the soda. But I've got to be careful, right? How many cans of soda are there? There's 12. And they gave me the mass of each, right? I've got to use the total mass in my equation over here, right? So this is 12 times 1 soda, right? Or 12 times, what was it? Did they say 0.35 kilograms? Yes, okay. But I don't, I'm not going to multiply the specific heat by 12, and I'm not going to multiply the temperature by 12. It's just, I've got 12 masses of soda in there. Each one with a specific heat and each one with a temperature. Okay, so I think we're good to go there. Again, what are they asking us for? The final temperature of the system, the soda and watermelon. So this delta T is going to be T final minus T initial watermelon. This delta T is going to be T final minus T initial soda. Did they give me the watermelon's at 27.5? Yeah, and the soda's at 4.74. Hey, we're good to go. We can solve for some stuff. Water C water plus mass soda C soda. All right, I need to get that T final out of here, don't I? That's what I'm after. I see it in 2 different places. but to get it out, I'm gonna have to multiply everything through. This is gonna get messy. And then I can factor, so this is algebra now, right? Mass of water, specific heat of water, temperature final, minus mass of water, specific heat of water, temperature initial watermelon, plus soda, specific heat of soda, temperature final, minus applying it through, don't forget any of my terms, there we go, aha. So there's my T final, there's my T final, this is gonna go over here, that's going to join it. When I move those over, they become negative, don't they? Negative watermelon, final temperature, minus soda, temperature, final soda, equals negative water, temperature, initial watermelon, minus soda, temperature, initial soda. Okay. I don't like minus signs, they scare me. So what happens if I multiply everything by -1? Since everything is negative, what does everything become? Positive. That's kind of nice. All right. What do I do with that T final over there on the left-hand side? I factor it out, don't I? Right? So that I get it all by itself, and then factoring it out, mass water, specific heat of water, plus soda. And then I got exactly the same thing I've got right here. The magic of iPads, we do that, all right? And then I can solve for final temperature, because I can divide both sides by this common factor that I've got here, right? So if I paste this right there and divide by mass water seawater plus mass, there we go. And I think I got all those numbers. They gave me the mass of the watermelon. They gave me the specific heat of the watermelon. Why did I start putting CCs? That's a W, that's a W, that's a W. Yeah, everything on the right-hand side is a number that was given to me in the problem. So, that one was mostly a math problem. What's how do you know when heat is being transferred by convection? Or to ask the question differently, how do you tell the difference between convection, conduction, and radiation? The two things have to be in physical contact, right? So when you walk outside and stand in the sunshine, is that heating by conduction? No, because the sun is not touching you, right? You're not in physical contact with the sun. So what kind of heating is that? Radiation. Can you give me other examples of radiation? What's that? Oh, microwave. Yeah, that's a good one. It's a little bit of a cheat though, because the microwaves don't directly deposit energy. They cause the water molecules to get really happy and resonate. But yeah, we'll say radiation for that one. Any other examples of radiation you can think of? A heater, right? So we got to be careful there, right? It would be like a space heater, like it's got the glowing coils in it, or maybe a flame in it, right? and you're directly seeing that flame. It's not like the heater in your house, right? The central heater, because that one is doing heat transfer via, it's not touching you, and it's not like radiation where the light's hitting you. So what's left? Convection. Convection is heat transfer by moving molecules around, right? There's some sort of convection current that is taking place where you heat up or cool down molecules at one spot and then you move them to another, right? To cause that heat transfer to happen. So examples of convection, you're looking for currents. You're looking for, like I just described it in air over the lake, right? The onshore and offshore breeze where there's a convection current. Convection is what gets the water on the stove kind of boiling. You have conduction. Well, it depends on your stove now, oops. Let's just talk about the water in the pot, okay? The bottom surface of the pan is the thing that's getting the heat, right? So the water molecules that are in contact down there are getting heat via conduction. But then those water molecules go up and the cold ones sink down to get warmed up and you get convection currents in the water, right? Different stoves heat via different ways. A gas stove is heating by radiation. It's the thermal energy coming off of it. Most electric stoves are also, again, by radiation. You heat up the coil and that electrical resistance causes the heat and that heat is radiated into the pot or the pan. There's a certain kind of stove called a induction stove that heats via magnetic fields. If you take Physics 2B, you'll learn about that. But most stoves are heating via radiation. And then the food in the pans are being heated by conduction if they're in contact with the surface of the pan. Otherwise, they're being heated by convection, either steam or boiling water or oil or something like that. So you want to have, right, those ideas and concepts in your head, being able to distinguish between the three different heat transfer mechanisms for that conceptual question on heat transfer.
Number 10 for shopping cart.
12. Number 10. You guys are being very organized today. You say problem 10?
Yeah.
Imagine a physics lecture hall. That's hard. With 100 students. Can you imagine being in here with 100 other students? Like not this room, but imagine that the room was the right size, right? Just kind of get lost in the crowd after 60. I have taught rooms of 300 students, not here, but at my job I had before, between graduate school and here, I worked at, taught at my alma mater, BYU, and 300 students out there. It was nuts. Temperature of the room, conditioner breaks. Wow, we know all about that too, don't we? 60 watts, imagine the energy goes into the room. Volume, we're making a lot of assumptions here, but that's okay. Calculate the room's temperature at the end of the lecture. So we're being asked, right, about temperature change, or at least the final temperature, okay? And we're also being given a heat capacity. So this is a calorimetry problem, okay? So what's the system look like? Well, we have a room, and that's going to kind of be like our calorimeter or our ice chest or the thing, right? They're telling us, right, that the energy from the students is going directly into heating the air, which isn't actually what happens. But we're just pretending for this problem. So the system I'm seeing here pretty much is exactly the problem I just did. It's watermelon and soda. where the watermelon is the students and the soda is the air in the room. There's two things, right? The students are providing the heat, right? The students cool off, right? They put their heat out, and the air in the room warms up, right? So I kind of don't want to repeat myself. Right?
When this one I did the same way I did it with the watermelon.
Yeah.
And it just didn't come out. Because the original answer I got was 20.7 degrees Celsius. But then the actual answer was 47.
Well, but the temperature should go up, right?
Yeah, that's why it didn't make sense. And I set it equal to 0, so 0 equals the Q of the students and the Q of the year. Yeah, it just wasn't working for me.
All right, let's see what happens. I'm game. The math should be identical. Let's see what happens. Maybe I'm missing something, but I'm not catching. So students, let's see. It's going to be the mass of the students times specific heat of a student. Oh, times maybe there is more here. Change in temperature of the students, because they don't give us the specific heat of the students, right? Ah. Okay. Imagine the energy released by each student goes into heating the air in the room. So, I don't know the specific heat of an individual student, but I do know the energy, right? They're telling me that a student outputs 60 watts of energy. All right. Knowing that it's 60 watts, I've got to go back to power now. And that was in the energy chapter. It's a 1-hour lecture. Power is equal to energy or work divided by time. We know 60 watts is equal to the energy divided by 1 hour. But I don't want to use hours, do I? What do I want to use? Seconds, right? So 3,600 seconds. So my energy is going to be 60 watts times 3,600 seconds. That'll be however many joules that is. So that energy right there, that is the Q that the students give up. Oh, that's Q for one student. What's Q for 100 students? 100 times whatever that is. Okay? So this Q100, right, is 100 times 60 times 3,600. They gave me the energy. I'm not trying to break the energy up into a specific heat or anything like that. They just gave me the energy that the students give off. And then I have the mass of my air, specific heat of my air, change in temperature of my air. What am I going to do for the mass of the air? What did they give me that can get me to mass of air? Yeah, they gave me volume and density, didn't they? So the density of the air they gave me was 1.220. 1.20. And then the volume of the air they gave me was 9.5 times 10 to the 2 cubic meters. This is kilograms per cubic meter. So my mass is going to be my density times my volume. So now I've got that. So Q100 is a number. The mass of my air is the density of my air times the volume of my air, both of which are numbers. Specific heat of my air, which again is a number right there. And then change in temperature. That's final minus the initial, which was 21. That should be it. Everything in there is a number, besides the temperature final.
Yeah, when I solved for it, I just got, so like what I did was, I multiplied my mass and my specific heat together, I got a number, and then I had temperature final minus temperature initial parentheses. So I multiplied my initial number into that,
Mm-hmm.
and then afterwards I got temperature final by itself. And it worked out for me.
So this is 21 times density of air, volume air, surface heat of air equals minus Q100, all divided by air. That should be it right there, if I did my math right. So Juan, I can look at it. Either send me a picture of it or just show me right after class, and we'll see if we can't find the error. But yeah, there's, they do it slightly differently, but yes, this is the same way. They found the total energy in joules. They do the mass per volume to find the mass of the air, and they just set them equal to each other. Which is what I did.
It's fine in my way.
But mine isn't as simple as theirs. What did I miss? What am I overcomplicating, or what did they miss? Always assume they're wrong. That's right, Mr. Balogh told me, always assume they're wrong. I stand by mine. What did they, where did they put their? Oh, there it is. Temperature initial. It was right. I can't read. 21 plus those things. They canceled a few more things out. That's all right. They kept mine in symbols. So we've got the same thing. So that we'll take a look at that together and see if can't troubleshoot it. Because I think we're down to a calculator problem or round off error or something. Oh, but you said it was like it was less than what you started with?
Yeah, because when I brought everything to one side so I could have a temperature final by itself, I was left with like the Q initial for the Q for the students was a negative for me after bringing it to the other side.
That's the same with mine.
And then I can just show you.
Yeah, because I ended up with negative Q students. Anyway, we'll figure it out. Because I think we're down to a math error. My most hated kinds of errors. Any other questions? Yeah.
Can you do number 8 for chapter 4?
Body must expend energy. Warming up the water, ice, burn, blah, blah. Suppose you expend that many calories. How many liters of ice water would you have to? Oh, okay. It's biology, so I'm suspicious already. But what they want us to do, right, is they kind of like equating, right? We've got a certain amount of energy, 420 kilocalories, right? and they want to know the amount of water, liters of ice water, in order to use up 420 calories. They're not asking it right. We want to change water from 0 to 37. We're going to take ice water and we're going to warm it up with our bodies. Okay? So the water is going from 0 to 30. So the final temperature of the water is 37. The initial temperature of the water is 0, right? So our delta T is 37 degrees. Okay. We also know that energy is equal to mass specific heat times a change in temperature. And we know the specific heat of water. It's 4,186. Okay? So, if we know the energy, and we know the specific heat, and we know the change in temperature, the thing we're solving for is the mass, the amount of water. And then somehow we've got to get that into a volume, right? The liters, because they wanted it in liters. All right. So, my temperature's fine. I've got it in Celsius degrees, which is the same as Kelvin degrees when you take a difference. The specific heat I know, it's 4,186. Q, 420 kilocalories. Can I use kilocalories in this equation? No, right? Because the specific heat is joules per kilogram degree Celsius. So I've got to convert 420 kilocalories, excuse me, into joules. So that's 420 kilocalories. Kilo means what? Times 10 to the 3, good. Calories, scientific calories. And then my conversion factor is that for every 1 calorie, I think it's 4.186 joules. That was right off the top of my head, it might not be right. But get the conversion factor there. That will give me the number of joules that I can then put on that side of the equation. Okay, then we solve for mass. Mass is going to be Q divided by specific heat times change in temperature. That's going to get us a number. But then we need to get this into liters, right? And the way we're going to get this into liters is that we can use the density equation. So we solve for the volume, it's the mass divided by the density. The density of water is 1,000. So whatever my mass is divided by 1,000 gets me my volume in cubic meters. And then there's a conversion factor which says 1,000 liters is equal to a cubic meter. So it's like a bunch of chapter 1 conversion problems, right? Getting all of these units into the units that we need. And then equating the amount of water to that temperature change. 11.4 liters. There's approximately 3 liters in a gallon, so that's almost 4 gallons of water, ice water. What would happen to me if I drank 4 gallons of ice water? Good grief. What's that condition called when you hyperhydration? Where you have too much water in your bloodstream, and marathon runners die from this every once in a while, where they'll drink so much water and then they'll go race, and the amount of ion concentration in their blood drops, and then basically nerves can't send information to organs anymore, and you lose nerve conduction and they die. Like literally their heart stops beating and we can't get it started again because they're waterlogged, essentially. On that happy note. As many of you know, I won't be teaching physics 2B. And some of you have gotten angry at me. Mr. Balogh, how can you desert me at a time like this? I'm not leaving. I'll just be teaching the Physics 4 series, right? And so if you are around taking class with our other teachers, they're great. I will be around, right? I'll be in grasp and all those kinds of things. So So please don't hesitate to reach out. One thing that happens on Canvas is that once like the semester's over, it like kind of cuts you out of the Canvas course, right? I don't know how easy it is to contact former students or faculty or anything via Canvas. So make sure you use my work email. You can find it on the website. It's my name at FresnoCityCollege.edu, right? If you need help, just reach out. I'm not abandoning you. Just my teaching assignment is taking me into the Physics 4 series where I've got to remember more calculus. That's what it boils down to. Whatever it is you end up doing, right? And for many of you, I know what that is because we've talked about it. You've told me about your dreams and your wishes. I hope that you've learned something a little bit more than physics in here. The physics is what the state of California wants you to learn. It's what all the UCs and CSUs want to see in your transcripts. But I've also tried to teach you other lessons. And I hope that one of the lessons you take away from this is that you can do it. That you are enough. That you have within you the abilities and the knowledge and the talents to keep going, to keep pushing. Physics has a way of showing where the cracks are and where your weaknesses and your strengths and all of those things are. I hope that you take that knowledge and you use it to the best of your ability to be successful, whatever you do. Thank you so much for an excellent semester. This is actually pretty much the first semester I've felt normal since the pandemic, where you guys came and you were into it. And I'm not saying the pandemic, kids were any dumber, they weren't. But we were struggling with so many other things and the distractions were just so there all the time that it made it difficult to concentrate. So I thank you for that. I thank you for your hard work and I wish you the best of luck on Thursday, right? That final day to you. Oh, thank you. And if I don't see you tomorrow, I'll see you Thursday. Bring your quizzes up here.
This is how you would.
Yeah, the total score on top. Savannah Bananas? That is amazing. You know that UCSC's mascot is the banana slug. UC Santa Cruz?
Oh, yeah.
Yeah.